This is the next chapter in our forecasting course, and I'm going to talk about traditional statistical univariate forecasting techniques. I'm following, so the standard resource for these traditional time series forecasting techniques that I somewhat follow in this part of the course is this book by Hindman and Athanasopoulos, Forecasting Principles and Practice, second edition. The second edition was with using the forecast package in R. The forecast package in R is now not developed actively anymore. There is a third edition that uses the Fable package in R, which is part of the tidyverse. And then there's also relatively new, this Python version that uses stats forecasts in Python. That is also a very, very nice and very good resource. Yeah, let's start off with a bit of forecasting terminology, because the terminology is usually coming out of a statistics context, and in machine learning, often people use different names. So if I say model fitting, parameter estimation, that would be model training for a machine learner. In sample is just the training set, out of sample is the test set. The forecast horizon, that's my target variable that I try to forecast. The forecast origin is from where you do the forecasting from, so it's the last known observation. A rolling origin now just means that this forecast origin changes for every point in the test set, right? So something like today I forecast for tomorrow. Tomorrow I forecast for the day after, and the day after I forecast for yet the day after. So my horizon is always 1 because I always forecast for the next day, but my origin changes with every forecast. A fixed origin is now a forecast origin that is fixed, and there then usually the horizon changes. So you could do a forecast today for every day of just the next seven days, so a forecast from today for tomorrow, the day after, the day after. So it's a 1 step ahead, 2 step ahead, 3 step ahead forecast. Forecast combination, that's what we usually would call ensembling in a machine learning context. Then we have lags, independent variables, regressors, covariates or predictors. That's what would be called features or inputs. We have dummy variables, indicator variables, that's one hot encoding. We have seasonality or seasonal period. That's a cyclic change in the mean of the series. And we would always assume that its length is known a priori and it will not change in the future. Right, so seasonality is something very powerful that we use in forecasting. The idea is a Monday is a Monday and has the patterns of a Monday. And if we now go 5 years into the future, it will still be a Monday and have essentially the patterns of a Monday. I mean, of course, we can then also let this seasonal shape evolve and so on. But yeah, the idea is that seasonalities don't change and you can reliably just extrapolate them into far futures. Trend, that is just a smooth change in the mean of the series. So I think here it is important, to also know that there is not really like a mathematical definition of what a trend is and a seasonality is and so on. So yeah, trend, it's just like a smooth change in the mean of the series. So usually you would just kind of smooth the series very heavily to say this is now the trend. Okay, so now let's get into some first very simple forecasting techniques. For that, I have generated here 1,000 normally distributed random numbers with a mean of 0, a variance of 1. I also fixed the seed value. What you see here is just some R code to do that. In Python, it's equally simple to do that. And now what we're going to do is we're just going to sum up these random numbers, a cumulative sum, and we're going to plot this, and this is what gives us now a random walk. Why is this called a random walk? Well, because at any point in time, you just take a random step, a step of a random size in a random direction. So in this case, either up or down. So now the question is, what is the best possible forecast for this random walk? So let's go back to our initial series of the innovations. So because we know that we sampled them from a standard normal distribution with a mean of 0 and a variance of 1. Now, the first question would be, well, if I say what is the best forecast, the question is best under what evaluation regime, right? Now here in this case, well, we know there are Gaussian innovations. So we know this is a unimodal symmetric distribution. So we know the mean, median, mode, it's all going to be the same and it's all going to be a 0. So I know that the distribution mean is a 0 and this is the best forecast under many different losses, right? Yeah, so under MSE, under the median, yeah, the mode, it's all 0. So the best forecast is a 0, but in real life, we would usually not know the distribution that this is coming from, so we have to estimate that, right? But because we know what we've sampled it from, the idea is now, well, instead of the actual mean of the distribution, we are going to use a sample mean. So we take our 1,000 examples, we calculate the mean over those. That gives us a sample mean, and you see here it's not exactly 0. Well, it's not, cannot see it very well, but you see the idea is, well, maybe after 1,000 samples, it's not an exact 0, but obviously if you now continued sampling, it would get closer to 0. So certainly the sample mean is the best forecast here. And it's also important that each sample is equally important, right? So these samples here, they are just as good to estimate this mean as any other samples here or the samples here, here. Okay. Good. So now, what does that mean for our random walk? So in the random walk, what we do is we do we would do what is called a naive or persistence or random walk forecast. So because we've just established that the best forecast in this case is a 0, what that now means is that we take the last value that we know, and we know the innovations are going to be 0. So basically this last observation as it is the best forecast, right? And so like mathematically, demonstrably the best forecast for this data generating process. Okay, and now what you see, and now one quite interesting thing here is, well, we see all of these dynamics here, right? And so you can already imagine that, well, so what we see is here it goes up, here it goes down, here it goes up again, right? And let's say this was a stock price, right? No, you can already imagine that people would say, oh yeah, well, it really went very well, the company up until here. And then it just all went very, very badly up to here, and down here, then the CEO made a change, decided something, and it all improved a lot. So you can find a lot of structure in here, where later in hindsight you could try explaining what happened there and why it happened, when the truth is here, because we've simulated this series, we know exactly what's in there. We know there is no structure in there. We know it's all just little deviations that are completely independent from each other added up. And you would probably now have a quite tough time arguing to your stakeholders that this is actually the best possible forecast and that you shouldn't do, for example, this as a forecast, right? To just say, this last trend that we see, why don't we just assume it continues into the future, right? Yeah, and another thing that we're going to get to soon is what we see here also is that the forecast is obviously not really realistic, right? I mean, like we all know that this time series is not just magically going to turn into this straight line, right? So of course it's going to wiggle around, but the thing is we don't know how it's going to wiggle around. So under things like, if we are interested in MAE, RMSE, then this is going to give us the best forecast. But we get back to that in very soon. Okay, and now another thing, I'm just always fascinated by the dynamics, by the rich dynamics that you can get out of these forecasts. So the only thing I'm changing now is the seed. So I've put now a seed of 2, and you see you get this kind of upwards trajectory with this thing that almost looks kind of like a seasonality, right? So you could really kind of read in a seasonality here that's clearly not there. Seed of 3, that's the one we've already looked at. Seed of 4, here it's just kind of going down, down, down. So, company that's really not going very well. This one is an interesting one as well. You get here again these things that look like seasonality, or maybe you could say these are business cycles. And then here this level shift and yeah, again, I mean, I can guarantee you that people would be very good with coming up with explanations in hindsight why you are going through these cycles, what we are seeing here, why you had here this level shift, when in reality there is no signal in here. It's all just IID, small random innovations summed up. Okay. So we've already seen now 2 simple forecasting techniques, the naive and the mean forecast. So the idea of the naive forecast is we use the last known observation as our forecast. In that way, effectively, we are weighting the last observation with a 1 or the other observations with a 0. So the only thing that counts is that last observation. Yeah, and the mean forecast, we calculate the mean over all the observations. Right, so that's quite the opposite. So all observations are weighted now equally. Even the ones very far long ago are weighted just as much as the one from yesterday. So naive and mean forecasts are 2 extreme cases. But a central assumption in forecasting is often that the more recent past is more important than the more distant past, right? So if you want to forecast, I don't know, tomorrow's weather, for sure yesterday's weather is more important than the weather from 2 months ago. The only real exception to this is seasonality, right? So if you have seasonality, for example, you have a weekly seasonality, then probably if today is Monday, then probably last week's Monday could be more important than yesterday, which was a Sunday, right? So the seasonality kind of breaks a bit this pattern of that always the last observations are more important. But even then, obviously, the last Monday will be more important than a Monday 8 weeks ago. Yeah. And now one idea as well, I mean, if we have these 2 extreme cases of giving all the weight to the last observations or having the equal weights, what about we just decay these weights in some way, and we could do that with an exponential decay, right? And that's the main idea behind exponential smoothing. So there is this method called simple exponential smoothing, SES, that implements that. So you have a smoothing parameter alpha, that you choose, and now you are basically decaying. So the smoothing parameter alpha is like a weight, and now you're decaying that weight with decay rate of 1 minus alpha. You need the alpha also be in the decay rates so that the weights all sum to 1 at least, if t goes to infinity. And so what you see here now is, so I've shown you here this red line. I've shifted it down from the 0 so that you can see it, and you see here this exponential decay in the weight that these subsequent observations are given. So the further you go back in time, the less important is the observation determined by this exponential decay. So what we see now here is that our forecast, it's still, so the last observation was here, our forecast is here. So it's still kind of anchored by the last observation, but it's not just exactly where this last observation was, but it's also taking account the past values that were apparently a bit lower. And that's why our forecast is a bit lower.